let's start with algorithms, because these are often easier to grasp and to understand. And I'll probably go relatively quickly through this as it's repetition for many, but I want to give you a chance to show me how much you remember or how much you know if you haven't seen it. There's many questions coming today. It's one of those topics where I don't have a good feeling for how much you know, so I'll keep asking you. So you'll have to tap a few more times. So let's try to do this one quick. And again, if you don't know yet, I'll tell you how it works. It's just the speed at which I tell you will be a bit dependent on this. If you haven't seen it, the same red book, I should have brought my copy. The red algorithms book, Sedgwick and Wayne, that is linked on Unit 2, is also covering all that we do in this first part. So if you want to read up the things at a reasonable pace for doing it the first time, that's a good source. Right, so most people, let me give this away. So most people get the second one. We'll talk about the first one too. And then there's a few with don't know, which again, that's fine. You may want to read up on it in a little more, in a calm moment. So let's do a quick rundown of Mergesort on the conceptual level. I won't show you full code for the merging part, but that's again done in the algorithms book by Sedgwick and Wayne's in full detail. Conceptually, what merging does is you have two parts that are sorted. So these triangles just should mean elements increase in value. They're already ordered. So imagine this is your array. Left to right is the indices, and the height is the value at that position. Suppose they are numbers. Again, the algorithms all just work for any type of objects as long as you can compare them. If I give you two, you can tell me which is smaller. That's all we need. But to make the examples easier to grasp, I will often use numbers or heights of bars. So the conceptual view of merging is you have two sorted parts. They're sorted within, but you don't know how they relate. And you produce one big output that contains all the elements from the two parts and is entirely sorted. How does this look like in an example? Here are two runs. Again, elements by height. Height is what we compare. And you see they are sorted. These just go up. And merging just can proceed like this. These are sorted runs, so the smallest element in each of the runs must be the first one. That's the one where these arrows point to. So we have two candidates for the overall smallest element, and we just take the smaller of the two. That must be the smallest overall. In this case, it's that guy. And then we can just move that to the output. So we copy the element to a result space. So that will be extra memory as a buffer that we use in merging. Once that element is gone, there's another first element in that run. So we again have to ask, is this one smaller or this one, by comparing them. And again, the first run is the one that wins. So we write that to the output. And we keep going like this. So this time, again, we compare the first of the remaining elements of the runs. This time this is smaller, move it to the output, and so on. And sometimes you can take a shortcut if you've completely exhausted one of the runs. The rest you can just copy over because there's nothing else to compare them to. And that's basically merging. Now that's not sorting yet. We already needed two sorted parts, but we could produce from two sorted parts one big sorted part. That's what we've done so far. Before we move on, let's again probe your memories or your general knowledge. Where is my question? So let me point out, this is asking for merge sort, the entire thing, not just merging what I showed you the example for. All right, looks like a very clear picture. So let me just give this away. Okay, I didn't, maybe I scroll down if there were more answers. That's an absurd amount of possibilities. I just put everything in that might remotely make sense. N log n is the answer. I kind of gave that away maybe by saying that sorting has this complexity. But it's good to remember. So hammer it in a few more times, doesn't hurt. How do we turn this merging procedure into a sorting algorithm? The abstract explanation is what popped up in the Slido question. You recursively sort the left half. You recursively sort the right half, then you have two sorted parts, and then you merge those. And the beauty of recursive algorithms is that that's all you really need to think about. And that's what this algorithm does. So merge sort is given some range of the array, and the first call will then be merge sort with the entire array. So starting at 0, ending at n, if that's our length. That would be the initial call. Then we determine if we're already done. If we have if we have a list of just a single element, nothing needs to be done because that's sorted in itself. Otherwise, we find the middle point. So if that is our array from L to R exclusive, then we find this midpoint M. And we recursively sort the part up until M excluding M, and the right part from M onwards, and then call the merge procedure that I showed you by example. Now, that merge procedure needs an output buffer. It doesn't work directly in the array that we're given, and doing that is actually possible but very tricky. So you can do that, but it's slow, and so it's not very interesting. The fast merging methods use some buffer area to write the elements to. And then here we copy them back so that we have this outward facing interface of sorting in place. Okay. That's all the code there is for it. And it's not hard to implement that in your favorite language. And I'll leave that to you. You can see it in Java in the algorithms book. I'm sure there's an easy Python implementation to be found on the web. What I want to briefly talk about is the analysis. Why is this n log n overall running time? Slightly differently from what some other books would do, what I want to count here is the number of element visits. And so an element is visited whenever it is read or written to an array. Now, that's very related to the number of comparisons. If you think about the merging procedure, you read through one run, you read through the second run in interleaved ways, and you write the output once. So the cost for a merge, when you have two runs of length n, if the output is of length n, then the cost of a merge is 2 times n. And that's true in the best case and in the worst case. It doesn't matter how the elements look like. They always have to be touched, read and written. If you count the number of comparisons instead, you get something that's between n and 2n. So maybe worth writing down, but The analysis then will continue with this element visits as the elementary operation. Sorry, between n half. I guess at least our merge procedure, it would check, is the first run's first element smaller? Yes, yes, yes. If the first run always wins, you exploit the first run entirely. That needs roughly n half comparison, the length of the smaller run. And the second run doesn't need any comparison, it's just copied over. So this is still roughly, or upper bound is n. But the math is a bit nicer if you do the element visits. So you've looked in the tutorials at recursive ways to express a function or a sequence of numbers. And that's what we'll do here for the analysis. We say C of n is the total number of element visits to sort an input of size n. And if the list is short, it's just a single element, we don't actually touch that element. We just return right away. So that costs us nothing. Otherwise, we do these two recursive calls. And if you work out how long they are, one is n half rounded down, and the other is n half rounded up. That's the cost. So we use the same function. So that's the cost for recursively calling us on left and right part. And then we add 2n for the merging. That's where this recurrence comes from. The second step is a pure math exercise, and you've done it a little bit in the tutorials for a simpler example. Here, one thing you can do is if you simplify by saying n has to be a power of 2, I'm only solving the recurrence for a power of 2. Then those two parts, the rounding always works out evenly, and you don't have to round. Then the recurrence simplifies to this, and you can actually spell out, you can explicitly say what happens. So you get the 2 times 2 to the k from the first part, from the merge at the very end of the algorithm. Then you have a first recursive call here, and that gives you this green term in the next level down. So you multiply it by 2, then you have 2 times 2, that's the 2 squared. But you go down in the argument by a factor 2. So that's why here, instead of 2 to the k, we only have 2 to the k minus 1. And if you observe what happens if you spell this out a few more steps, you see that that's always the same thing. You add a power of 2 in the front, and you subtract a power of 2 in the argument. So all of these terms are actually the same because the powers just add up. And so it has a nice closed form. If you reinsert, if you solve this for k, then you get k is log n. And inserting that gives you this solution of 2 times n log n. Strictly speaking, that's only true for powers of 2, right? So if you want a strict upper bound formally proven, you could say this function is monotone. It costs more to sort a longer list. So you can bound C of n by making n artificially larger, going to the next power of 2. And so you get an upper bound, which is a factor of 2 away, but it's still n log n. Now, just because it's so cool and I want you to know, you can actually solve this recurrence exactly. It doesn't at all look like it because of these weird rounding ups and downs. It feels like that's complete chaos. But no, you can handle the chaos and you get this precise solution. It's an equality, no approximation. Where you have the basic term that we found as well. The 2n log n shows up as the main term. But then you have a term 2 times n multiplied with something that's, I guess it's between 0 and 1. And it fluctuates depending on how close n is to a power of 2. Okay, that's just a piece of trivia. Treat it as the fun bit of that slide, and you can otherwise ignore it. But that's Mergesort and its analysis, where we've used recursion to write the algorithm and to write the analysis. So knowing already that this will be the optimal time complexity, what speaks for Mergesort is that even in the worst case, it has this n log n complexity or upper bound for its cost. It happens to be a stable sorting method. That's something we haven't talked about. It's still true. Stable means if you have elements that compare equal. So A and B, A is less or equal B, and B is less or equal A, which you could say A and B are equal. That can happen even though the things are not identical. So for example, you could have a list of people sorted by age, but they could be born on the same day or say same year or whatever, but not be the same person, right? So a stable sorting algorithm would keep objects that are identical according to the sorting criterion in the order they've been in the input. And that's useful if you sort complicated objects like people several times. So you could sort a list of people first by their first name, and then sort that list by the last name. If you do that with a stable method, you will get a list that's sorted by last name, and among those with the same last name by first name. And that can be useful. If you do that with an unstable method, if you sort by the last name of the second round, it might scramble the order of the first names again. So Mergesort is easy to make stable by when you do the two runs and there's a tie, there's the two first elements that are equal, you just take the one from the left run and give that precedence, then you're stable. So that's good for Mergesort. Another thing, this is getting a bit more technical. We talked about our model for computers. We said, okay, all we do is on the RAM, on the word RAM abstraction of a computer. Now, of course, we still have to eventually use the computers we can actually build, and they are not precisely that model. In particular, they have caches and a memory hierarchy. And so if you care about the performance in practice, it's another benefit of Mergesort that it uses memory in a sequential way, basically scanning left to right, jumping one step at a time, instead of randomly jumping around. And that just happens to be faster because of caches. That's not really something you need to know deeply for this module, but I thought it's useful to throw out. Now, Mergesort has one big downside, which is that it needs this buffer space for merging. Remember, when we take the two runs, the only easy way to do merging and stable is to write elements to a buffer array. And that means we need extra space. I mentioned this before, there are ways to work around this, but they're mostly theoretical curiosities, not so much relevant in practice. So there's, as a puzzle, you can do merging in place and stable with complicated recursive tricks, but it ends up writing the data many times, so it comes at a prohibitive cost. But it's possible.